for a given variable, which is a reaching definition analysis, right? So that way I can find for the given use, right? So that's diffuse chain analysis. For that means that once I define something, then those are the use, right? That's why if I change the value, then those are the ones that are affected by the change of values, right? So the data analysis reaching definitions basically the basis for the data dependence graph building process. And we talked about the control dependence a lot in the last lecture. So what is the fundamental analysis you got to perform to get the control dependence information sorted out? I don't see a kill today. Oh, a kill right there. I'm sorry. Yeah. Yes, I'm just asking. So, what sort of analysis do we need to build up to figure out control dependence information? Yeah.
Will you do the backwards flow now?
So that's something that we do over the proven dependence graph, right? So this is basically the in the middle of the proven dependence graph. So we already figured out this data dependence graph. Then we need to build up this control dependence graph, right? This is just the graphical structure where you basically encode this control dependence, right? So what is basically the key points of this control dependence analysis? We talked about two different ways, right? There is some compiler implemented one way, the other compiler basically implemented the other way, right? So one way, we basically take the original control flow graph and rotate 180 degree and flip the control flow x directions. That way, what do you get? Reverse the control flow graph or CFG. Then we do our super famous concept of analysis, dominance frontier. So you basically run your dominance frontier implementation path over that R reverse CFG. Then what you get as a result of dominance frontier is the control dependence information upon the original control flow graph. And that's the one way we talked about. And the other way we talked about, all right, so we just take the original graph, but this time we build up post-dominance tree. And you know, to do the dominance frontier analysis, you need to have a dominated tree, right? So if you actually remember the relationship between the dominance and post-dominance, by flipping some variable in fraction of the original algorithm for the dominance frontier calculation, you can easily turn that into the control dependence analysis over post-dominator tree. So those are the basically two ways we basically systematically build this control dependence graph. And in this lecture, we're going to actually take a more on this slicing, but I want you to think about the other type of gradient. So what we have took a look at so far is so-called the backward slicing. So then, do we have a forward slicing? So if you basically extract some code from certain criterion by following these proven dependence edges, you know, that's regular way. So our backward proven slicing is technically basically navigating proven dependence graph backward, right? By following mechanically, you know, these incoming edges. But what if we just follow these outgoing edges in a regular order? Maybe that's the way we can get the forward slice, right? Then what does it mean to have the forward slice? Why you need such a slices? So there's something that we want to think about in this lecture. And then we do this slicing within the functions. So that means all the interesting code in your program statements, which is part of your program slicing criterion, all following the same procedure with the same functions, right? But what if I have multiple functions and the code that possibly affect my variable in my pricing, the slicing criterion might be affected by a whole bunch of the statements that are spread out in all the functions, right? So that means your slicing analysis must be extended into interprocedure analysis levels. So if we need to do it, then can we just use the proven dependence as is? Or do we need to somehow expand this structure that captures this control data dependence analysis information result somehow so that it can take care of this dependence between or across the functions? So those are something that we need to think about. So this is a kind of the canonical form of open pattern leverage. So we're gonna build upon the simple code, and we start with intro procedural slicing again. So this is a control flow graph, right? But it's kind of different from the one that we have seen before, because all the nodes right here, it's not the base block. It's rather statement. This is called the statement level control flow graph. But it perfectly makes sense, right, in the context of program slicing, because slicing itself, what's your criteria? Always interest program variable V at certain line of the code, P, or your program point of interest. That specifically point out a specific instruction of the statement within some base blocks, right? So that's why the statement level control flow is kind of making sense in the context of program slicing. All right, this is kind of our starting place right there. And then to build up, once again, the program dependence graph, which is just a mere combination of control and data dependence graph, we start up with building control dependence graph. Again, we have two different ways depending on which compiler you're going to use, right? But anyway, you figured out by applying dominance frontier over the reverse control flow graph, or you just directly calculate this control dependence information in the original graph with your post-dominated tree. Either way is fine. But this is basically the result. We basically encoded control dependencies right here. So meaning these two instructional statements control depend upon this while the predicate is the condition. And the all things is T, that means, right, enter means kind of a start. The program start. So of course, all these statements are guaranteed to be executed. But not these two guys, right? There is a way you can completely bypass the body. That's why these guys are not directly control dependent upon this guy. This guy is only control dependent upon the predicate, or here in this case, the iteration on task. So that's the step number one, to prepare the approved dependence graph. The next step is to figure out our definition chain. So this is a part where you need to apply a reaching definition analysis. For a given variable, the I is defined. This I is basically the use right here. And then I is just used in the induction variable of the bodies as well, right? So let's take a look at this pre-nap just for a moment. So we refer to the I, right? So how many incoming answers do we have? All right, they're coming from this I's induction variable update. We might want to correlate this thing, the part, corresponding part of the code right here, okay? But the other actually, if you follow right here, then you're actually going back all the way to this I's initialization code. So right here. Does it make sense? Yeah, again, there is a possibility you can completely bypass the bodies, right? Then this I, if you're talking about this thing in the data flow analysis sense, can reach out to these places. And this one also reach out to these places. If we have two different reaching definition set, or your resulting data flow information right there, how are we going to merge? Applying mean operator. So what is the mean operator for the reaching definition analysis? Unions. That's why we say two things basically affect this guy. That's why we have a two outgoing adds all the way down to the pre-nap statements. Again, that's nothing but figuring out the definitions. So once again, so PDG is basically the merging these two things together. So just to differentiate control dependence attributes from the data dependence attributes, we use two different colors. So then we're pretty much ready to do any slicing for any given slicing criterion. But before we go to that point, I'd like to point out this is somehow abstracting away the property of the program. So one typical thing right here is the order of the instruction. So initially we had a in some followed by I's initialization. But here, purposely, I flip the order. But still, you get exactly the same shape of program dependence graph. So order doesn't matter. This part is, that's a property of programs, right? Is abstracted away. Why? Because program dependence, so what it cares about, always about dependence between the statement and its value definition is used and the control dependence. Any other properties of the program, we don't care. That's why even though you flip the order of the instructions, you still get to exactly the same shape, the proven dependence graph right here. All right, so now we're ready to run through these examples once more. Let's say I'm particularly interested in this part. Again, your program slicing criteria is always paired. One, which particular program variable I'm interested in. Let's say here in this case, I'm interested in the I, okay? So then you now need to figure out, all right, if I'm interested in the program value of I at this very program point of interest, and which are the instructions or preceding statements that can possibly influence the value of I at this very point. I mean, your I could be used whole different places, right? But depending upon where you basically ask for this query, your resulting slice might be different. That's exactly the same as the way we actually make the query for the compiler for the data analysis results, right? So this particular point we're interested in I's value, which one basically factoring the values of I? That's basically proven slicing BD. All right, so how are we gonna do that? So that's a slicing criterion that where we know this is a starting place, right? Again, your slicing is technically the following these dependence edges over the program dependence graph in a backward manner. Backward means for a given slicing criterion or corresponding node in the control flow graph, we basically do the backward traversal by mechanically following these incoming edges with them marked. Because at the end of the day, we need to basically the all marked one as part of our resulting program dependence graph. So enter, that's kind of an imaginary node, so we don't care. And then that one has once again two different I's data dependence as definitions. Again, simply because our reaching definition analysis mean operator is union, these two can technically affect the use of these I in the printf statements. All right, so that's why we basically mark these three things by following one level of these backward or edges backward, right? So then we do the same thing, all right? This one, does it have any incoming edge? No, we cannot go further. But what about this one? All right, so we have incoming edge, but we already marked, right? And then any other things, I don't see any incoming edges for this guys as well. But this guy, all right, it seems like I have this incoming edge, which I already marked, but then this one has a control dependence edges right here. That means because of this guy, I need to mark this thing. Then if I mark this thing, that means I need to figure out whether this guy that I just recently marked has any incoming edges. So that means you need to do this backward traversal again and again, recursive fashion, until the point there is no further way you can go down. So that's why we already marked the wild right there. And does wild has any incoming edges? Yes. So enter, we already marked. And we have a self edges right there. And this one's already marked. And then this one's not the incoming edge, already marked. It seems like there's no further things we can go further. So then, anything that we have not marked, what does that mean? At the end of the day, when you get out of these backward traversal of the nodes over the proven dependence graph, the only nodes you have marked, you visited, those are the ones that eventually get into your resulting slice. Anything else you have not marked, that should not be part of your resulting slice. So we have this form, and then we just get rid of all the other things have not visited. So that means compared to the original code, we have a less shorter amount of the code in there. Again, slicing is kind of extracting something you're only interested in, right? So usually at the end of the day or at the end of the slicing, you will get a smaller code. And these are exactly the statements that affect your program slicing criteria. I'm interested in the I's value at this very point when I'm calling these three. Then only these codes are the ones that can technically influence my value. Again, at this very point. All right, that's a backward slicing, right? But then for the same pair of these program slicing criteria, or I'm still interested in the value of a program variable v, right there, exactly the same program point of interest. I still interested in the value right in there. But then now, I'm interested in slightly different kind of a subset of a program. And this is technically the way we define for the slice. So if I have some value in that very interesting program point P, then if I somehow change the value, then which part of the code of the program are going to be affected by this change of the value at that very program point I'm interested in. Okay? So that means I make a change. What is the kind of ripple effect of my change? That's basically what your forward slicing is trying to give you. So that's your faucet. That's your program slicing criterion. Because of your data changes, values of changes, you basically have a ripple effect. Then some part of the code might see the changes, meaning they're affected by the changes, right? You can forward slice. If you see some statements at the end of the day resulting forwarding slice of that criterion, that means that anything that you see in this forward slice is the one that are going to be affected by change of value at the same program point. So it's literally ripple effect analysis. All right, so let's say we kind of shift our point of interest to the very first lines or some initializations, meaning again always pair. That's a criterion, right? We are interested in the variable here, which is sum, the line number 2 or the first initialization. That's basically the way we form the criterion. And then I'd like to figure out which one basically part of these forward slice corresponding to the slice of criterion. So meaning once again, if I change the value of it, then which ones are basically seeing such change? Can anybody tell me? Yeah, we're gonna figure this out, right? Which one? I mean, tell me, which ones? So we're doing ripple impact analysis. You make a change right here, 0 to 100. So which ones technically see that effect? Say it again? Yeah, be precise. We have a sums reference in there, right? They will see the values, of course. And then they will see the value of the PNAP statements, right? So eventually we're going to find these 3 statements as a ripple effect analysis results, right? And these are the ones you're going to find by slightly different type of a program dependence graph perspective. Still the same, exactly the same form of the program dependence graph, okay? So you don't have to have some different kinds of program dependence graph. You can reuse this program dependence graph you once used and you once built for the backward program slicing. But then the way we traverse right here is completely different. Previously, for the given slicing criterion or the corresponding nodes in the control flow graph, we mechanically following incoming edges. That's technically a backward traversal, right? This time we just do the forward traversal. Rather than following the incoming edges, we're just following the regular directions, just outgoing edges. And still, you do this thing again and again until you can do further. This is recursive, the forward edges traversal of program dependence. So again, sum equals 0. That's the basically corresponding nodes in the control flow graph to our criterions right there. So we have 2 different outgoing edges. Sorry. So this one has 2 different ones. So this one is already marked. So technically we have a C shoulder mark. But then we don't have any further outgoing edges. So these 3 are the ones that should be in your slice. Okay? So then the interesting question is, I don't know whether we have a time to address these things that, let's say I have 2 different slicing criteria. Okay? So let me, let's say you have some program point, and I have a slicing criterion 1. Okay? And And then some of the program point have a slicing criterion, the 2, right? So then to the first slicing criterion, I'm doing whatever it is for slicing analysis. So then let's say you have a whole bunch of code in between, but any code, any statements within this region of, let's say this is kind of my way to include all the statements that is affected by this ripple analysis, ripple effect analysis from the first slicing criterion. So that means any other statements that are outside of these regions, the slice, is not part of a ripple effect analysis result or slices, right? So then I'm doing the opposite for the following ones. Now this one, I'm just applying backward slices, okay? So this time I'm interested in the technical effect, my values. That's completely opposite of the way you build another type of slice, right? For a slice. So then you can do the same thing. Well, maybe I can just draw this way. So that means that anything that outside of this kind of opposite triangle is not possible to affect my values in my slicing criterion 2. So then, here in this case, we have some interesting region of these slicing statements. There are overlap between these forward and backward slicing. What does that mean? If you found something, if someone's trying to answer by ringing the table. So I'm not sure we have some time to discuss this thing, but this is called program chopping. And then the whole purpose of these combinations of forward and backward analysis is trying to calculate the overlap region for 2 different program slicing criteria. So finding the value that can pass information back and forth between these 2 slices. So if you find anything that means that is the kind of the value, you need to treat something important. The typical example is the debugging process. You kind of go back and forth to 2 different ways, 2 different proving points, right, to figure out some things, right? So that means that anything that is in this overlap region is the one that you have to prioritize to debug. Okay? So maybe that could make expedite your debugging process. So alright, so now we're talking about the inner process analysis. Once again, I have some slice criteria, but the code that can possibly affect my value in the slicing criteria might be found in some different places, all of the other functions. That's why we need to do this analysis across the functional procedure. That's why we call this as inner procedural program slicing. Again, the main question we had in our mind is that the program dependence, which was the basis for this intra-procedural program slicing, is something that we can build upon still for this inner procedural analysis. And if we need to somehow extend it, what would be the way? Again, this is a cross functions slicing analysis, right? So then if you need to extend this original program dependence graph, what sort of the characteristics of a function invocations or returns you gotta encode into this new graphical structure that we call system dependence graph. So before we talk about this new form of basis for the interpersonal program analysis, which is the SDG system dependence graph, let's take a look at sort of motivating non-conformed examples right here. Same code, right? Technically, but we have the function calls in there. We already see the 2 different functions. So anytime you see criterion, anytime you have certain instruction found in the other function as part of the slice, that's already in a procedural analysis, and we have a function calls right here. So that means that there is probably the chance to propagate these dependent information across the functions, right? And then this communication between these 2 functions right here, the callee and the caller, or the call side right there add. So how are we gonna basically, or what information do you need to keep in your extension of a program dependence graph, which we call system dependence graph? So let's say we still interested at this very point, the proven value or variable I right there. So then, which one is going to be in, or should be in, the resulting slice? People, can you try?
Sorry, what is the question?
Alright, so I'm asking, so I have the slicing criterion right there to tell me the slice. So which instruction should be in the resulting slice of this criterion?
Right, so all the ones do with I.
Okay, so we can find something in the interrupt procedurally that's done, we already did it. So now the tricky point is we have a communication between these two functions, right? So this is basically the resulting slices. I know, Gabriel, if I give you enough time, so you would probably told me these things. But here the tricky thing is that I don't know whether you encounter this thing in your mind. All right, we have a functions, right? So that means, like in the control flow graph, there must be certain connection between the data flows, right? Same thing with control dependencies as well. So that means here in this case, I invoke this function with these two different parameters, the sum I or I1. Those are the way you cosine pass this data to the function through this formal parameter. Or if you think about this in the cosine manner, then that's the actual argument, right? So this is basically data flow, right? So that means there must be some way we can capture this data flow or dependence in our system dependence graph, okay? And at the same time, when you actually go right here, or proof control is already at the end of this function being invoked right there, then there's not a communication is happening now. The result of the function in this case is getting back to where? Where the function we call that's technically the call side, right? But we have two different call sides. You gotta be careful which one do you need to connect, okay? And technically you have a function, then you technically call any different places you want, right? So then how are you gonna basically summarize all this information by slightly extending this proof dependence graph? So by the way, you might want to compare these two things right here. So this is the actual precise slice result of the criterion at the bottom of the prenet I, okay? But if you build your kind of extension of proof dependence graph, or you have a system dependence graph, but then you do, let's say, this proof dependence as tracking or system dependence as tracking, in careful manner, you might end up including these two irrelevant instructions right there. So I would say that's a precision loss. Of course, those two instructions has nothing to do with the value of I in the slicing criteria, right? But depending on how you're gonna do it, you might end up having those two things, even though it's irrelevant. So that's something that we're gonna carefully take a look at.
When you're calling the function, if there's more code which doesn't use XOR, would the other code be also included in the backslice, or would it just be?
It always depends on when you pass the value, that is coming back to the call side, and eventually that affect your variable in the pricing criteria. But in your example, let's say I pass the X, but it doesn't use X at all, that means it doesn't affect technically.
So we won't take the back edge to the function itself.
No, that's basically part of the system dependence graph which is coming. Yeah. So you might want to actually just take a little bit of moment to see how we might be able to having these two structures. So once again, we have two different call sides, right? Again, I have a call, then I have a callee. I have to somehow connect it. Otherwise, there is no procedural analysis, right? But then you have so many probably call sides. Are you gonna assign a separate control flow graph for every single call site? Maybe that's not the way, right? Because you can technically call your function any different places, right? So in general inner procedure analysis, but we're talking about this in the context of the slice of force, but in the general cases, we basically assign a single control flow graph per function. So that means whatever the function f can be called 4 different places. That means for every single call side should have connection to the same single control flow graph per corresponding to these functions. Okay? So then if you have such a kind of a multiple call side into the same single control flow graph or part of the program dependence graph for the app, and then you have the same return actors to all different call sides. So then you could probably start to see the problem. Maybe this information kind of mixed up together. Even though I call from the whatever the sum equals add, whatever that information which is a result of the add might be propagated not only to the call side of add where I started to call this function, but also to the other call side because I have a connection there, right? But that's a kind of a source of the imprecision. Of course, we need to solve this problem, and whatever that the two boxes which result of such imprecision is something that we need to, bypass, right? We need to rule out those two irrelevant codes. So that means even though we assign one particular part of program dependence group or the one control flow graph for the function being called, even though we have so many call sides, we need to somehow differentiate these multi to one call side and one call side, sorry, one return side back to multiple call sides. So this is a kind of the place where we might have imprecision. That means you need to somehow address still with a single shared control flow graph of the add function being called. So many call sides. But the way we can do it is still starting out with the system dependence graph. So I think it's good to have how we're going to basically differentiate our program dependence graph for the system dependence graph, which is the basis for this inclusive program analysis. So as this is kind of a mere combinations of the PDGs. So PDGs are mere combinations of a control dependence graph and the data dependence graph. And then each function has its own program dependence graph. And the system dependence graph is basically, just grouping or merging every single program dependence graph. But when you merge, of course, you gotta be careful. Because let's say I have a program dependence graph for the main, I have a program dependence graph for the, let's say, the foo, then they call through call side. And then your call information or the result of the function being called basically pass back to where you made a call, to the call side. That's why each call side and the program dependence graph of the function being called has some special node for this parameter communication, for this return value communication between. Of course, we have such special nodes, and we have to connect it. So maybe this is a better way to say this. All right, we have a main function. So all the other things, they kind of abstracted away. Okay. So what it matters is basically in our function, our sum code, we have two different add, right? Let's say the function is basically the p. Okay. In the main function, I have two different call side p, call p, call p. So each call side, having these special nodes just to tell the main function, you might have a program control change to the corresponding target program dependence graph. In the same way, whatever the program dependence graph of the function p being called, we have these special nodes. Okay, and then for each program dependence graph has a procedural parameter. This is basically the arguments. Even the main function get the arguments, right? And this function p get the arguments right here. And of course, we return some things, right? So that's why we have a special node for this return, which is only the pink nodes right here. And of course, these special nodes must be connected to corresponding nodes right here. I have these special nodes for the parameter passing, have a node, special nodes to get the function result. So that means that this is something that is relevant for this function call or the call sites right there, right? That's why we have this connection to these own special nodes. Same thing is with this function. I get the parameter through this guy. and then I get the result, and I'm passing through this guy, right? So of course, when this is the result part, right? When it's basically going there, well, whatever the guy that gets, let's say, x equals foo, that means whatever that is foo's return value, basically pass to the x equals foo's places. That's literally the call side, but we want to separate this parameter part and the return value part because that's technically two different data flows, right? That's why we have a separate nodes. But this is basically preparation for building or for merging multiple program dependence graph. Getting merged already with the special node and intersection that we call this one as system dependence graph. Just merging the program dependence graph with caring about this communication between the function and the other function that's the function. So this is a resulting system dependence graph. I know the slides is getting crowded, but it's not super hard to understand. Still, we have the same code right here, and we already saw the program dependence graph for the sum, right? That's exactly the same. But simply because we have a call, that's why we have this call special nodes. And so every call may be propagating some value through the parameter. That's why we have a parameter nodes right here. Okay? This is basically I'm assigning, when I call the add, I'm basically preparing these two parameter x and y. We already know this add function takes x and y, right? And if you take a look at these function parts over the callee part, again, we have two different parameter x and y. Where they're coming? From these two different call sides right there. That's why we have the connections right here. Okay? But if you pass two values internally in the add function, that is basically added up, and the result is basically returned. Where do you go? Still the where you make a call to this guy. We have this one out, we have this one is another call side. There we get the values, right? Sum equals add something. So this out, which is a result of this, or return value of the function, is going to be assigned right here. The same way we basically I equals whatever the add function. Whatever that output you eventually get for the I is the written value of the function here in this case add. We just assign the special nodes for this parameter and written value communication. And once you assign such a node in these two different program dependence graphs, you just map it. So this is the shape of the system dependence graph. Now we are sort of ready to do, please.
Why is there blue arrow between the collat and xn, yn, and sum? Wouldn't that mean?
This is actually the control dependence graph, right? So let's think about the enter main. Why we have enter main? If program starts, then all the other things below the enter main with these blue outgoing edges are automatically or guaranteed to be executed, right?
Yeah.
So that means if you have the while loop is executed, which is code is basically technically found in the loop body of the while loop. So we have a control dependence. That's one deal, right?
Yeah.
And then if you get to these call functions or add functions right here, that means you're starting a program for the add, right? So that means if you already call this thing, then all these relevant call side or function invocations are guaranteed to be executed as well.
Yeah, but what's the other path that we're taking?
What do you mean by what's the other path?
Yeah, so like at the control dependence, we had to have like an option between.
Yeah, like the Y cases right here, depending on the path.
Yeah.
So we had a kind of a rule that if you take one path, it is guaranteed. You take the other path, it may or may not.
Yeah.
But then this is kind of a special case, like the start case. Again,
Oh,
function
okay.
gets started, then it's automatically. So I kind of omit all these, control flow predicate over these blue ads, not to make the slide crowded. But you can imagine all these things, top one, OT, that's guaranteed, no brainer. If program starts, they're guaranteed to be started. Same thing, call add means I'm gonna call this new program. If the program started, then everything is guaranteed. So that means you can imagine whatever that omitted predicate part is OT. Does that make sense?
Yeah.
Thanks for the question. So we are ready, please.
If we have no data dependence between the
Say it again. A little bit louder, please.
If we have no data dependence between the parameters and the arguments, or just there's no sum of I
There is
not
no
used.
possibility like that. Again, the actions right here, I pass the parameter. Again, so I'm technically passing the value to the function, right? So that means in my system dependence, there must be some methodology to do that. This is basically the axis between the parameter of the cosine and the arguments, or the other way, arguments of the cosine and the formal parameter nodes, which are special nodes, for the function being called in their corresponding coordinates. So that means this is always the case when you see communication.
But if those arguments are not used in the function, can we not eliminate the useless function form?
You can do it if you have additional analysis. Yeah. But do we need to? Well, I don't think so, because if there is no dependencies, then probably we don't follow, right? When we do the traversal. But if you already eliminate, then your intention is clear. All the program slicing that I'm going to actually give, or the slicing criteria that I'm going to give the compiler, is always bypass this unused part. That means you just omit it. That means your old criterion has nothing to do with whatever that omitted part. If you have that strong assumption that, then you can actually omit. That means that way you can save a little bit of time for your program dependence tracking. That might be a little bit faster. Thank you. All right. So again, this pretty much crowded. So I still wait on all these things after for this interpersonal program slicing. Still, this is basically the par. We had a slicing criteria. What was that? Our pre-nap of I. I'm still interested in i's value at that very program point of interest. Okay. Then, like the regular program dependence graph, again, this is nothing but just mere combinations of a different program dependence graph for the function with a special care about this parameter and written down communications, right? We're still mechanically following these incoming edges, meaning we are interested in that word, not the word slicing right here. All right, so we just follow. I have one incoming edges, and then I have two incoming edges right here for this guy's point of view. So that means to have the slice for this pre-nap, I should have this colon as, okay? And this is P, but you can take that as add function, okay? And then that one has down. Okay, so this is why I have this one. I have a add result is assigned in I. That means I need to have a add functions written down as right. And this was right here pink. It's a special mode we assign for the functions independence graph to capture the result of the function. Which makes sense. And then we follow again. I have some internal code that updates whatever the parameter, meaning if you pass the x and y, then we eventually add it up, right? That's probably the whatever they know that has data dependence for the additions. Again, the whatever added result should pass to the written value, and then we'll pass it into call side where you call. Makes sense, right? And we're still following this incoming edge until we cannot go further. Then eventually we get to this parameter point. And then now we have two different outgoing edges right here. So this is a part we gotta be careful, which would otherwise lead to the imprecision we talked about before. You already know if your criterion is found the pre-nap of the I, what if the sums initialization code and the sums update has nothing to do with the program value of the I at the program interested point, pre-nap of I, right? We already talked about that. We know that. But depending upon how you're going to deal with these two paths, which one you're going to follow, you might or might not include those irrelevant code in the resulting slice. People, which one do we need to follow?
We only follow the one that which we went through the output of.
Yeah, so that means even though we have a connection we should not follow, if we start from the this adds, let's say this is basically the one that we actually found initially, right? So if you study it this way, that means you should not go to the other part right there, even though there is a connection there, okay? If you don't want, that means the only way you can get around this problem is you need to have this entire control flow graph, data dependence, control dependence, program dependence graph for every single cosine, which is not scalable, okay? So in the general sense of interpersonal analysis, we don't do that. But still we have a problem, we gotta solve this problem, right? But then the entire problem is basically caused by a mismatch of this cosi and the co-return. It's kind of a problem is diagnosed so easy. But what if you have many different functions, okay? And even this function is recursive, that means depending on some predicate of the if then else, that you might call yourself again. So then it's really getting, complex. How are we gonna basically figure out such a complication? Which one is basically the right path that can be ever executed? So then this examples right here, the path is something infeasible, unrealizable path. I mean, if you call from the cosi right here as I, then you will get back. So cosi means right after the function call, I should be back to the same place. So technically the next instruction right after your function calls, right? So that means there's no way you can get to the add function to the sum, right? That's an infeasible or unrealizable path. Again, still we know how to get around this problem. We need to match the function calls and exit. But then the problem right here is there could be the case we have a whole bunch of functions in between, probably some other functions, right? Then all functions are basically mixed together with a recursion, with a control flow complexity. So that means you need to have some systematic way to catch these things. You need to have some way to catch this realizable paths from unrealizable or infeasible paths, right? But then it happens to be the case, we get the idea from very first step of, sorry, let me take that back, the second step of the complex workflow. What's the first step of a compilation? This is the kind of question that I'm just giving the whole credit to the undergrad compile exam, but anyway, maybe I should have the same thing. Here.
I mean, technically, isn't it the preprocessor?
Oh yeah, that's the zero step I said, I'm sorry. Yeah, the lexing, we basically, I mean, in the compiler's point of view, everything is just random character sequence, right? But some combination of characters meaningful. That's tokenizing, the scanning, the lexing. That's the second. We have a series of not the tokens. What do you do? Syntactic analysis, and then the other way, or more simple? Parsing it, right? Parsing based upon certain grammar, that's a basically theoretical foundation that allows you to do this process systematically, right?
Mm-hmm.
Then the way we basically differentiate these feasible call paths from the unfeasible, unrealizable paths is we can get some help from the parsing. That's very interesting, by the way. So again, what is basically the key problems or fundamental problem of these things? Mismatch or unrealizable paths. The function call and the corresponding function exit or return is not matched here in this case, right? So that means what would be the case where we somehow enumerate every single cosi, okay? And then we assign the specific symbol for each cosi, okay? And so we have two different ends right here. For this guy, I'm gonna assign, let's say, a parenthesis. And the other guy, the other cosi, I'm assigning bracket. Maybe I have a third one. I have some variant or, arrow, whatever. I assign some different brackets or variants of the bracket. And whenever we encounter the return, then we know corresponding type of brackets, right? Then we see over the path, these symbols we assign over the path basically the part of the language we're gonna design. This is a part we kind of skipped. You didn't do the homework for the parsing. But then if you have some interest, if you take a look at the code or our language manual, we have a whole bunch of grammar rules, right? But what kind of language do we need? It's a matched parenthesis language. That's basically all we need, because the problem right here is caused by the mismatching function invocation, the function return. As long as we can assign unique parentheses or the types of variants of bracket to every single call site and return correspondingly. Then whatever that symbols you see over the path will form the language. Sometimes that is exactly part of our master parenthesis language, which is a feasible path. But anytime by the grammar for this master parenthesis language, which I show you soon, doesn't take the path like this. It's not matched language. Then we don't bother. This is a way we can keep so-called context sensitivity, even with single control flow graph per function, even though it got called in so many different places. Does terminology like context sensitivity make sense? This is literally context examples, right? So I'm calling this guy, but which context are we talking about? Did you call this guy from first call side, or your context is basically second call side? It's literally called contextivity, right? So whether or not you basically care about this calling context roughly, you might or might not rule out those irrelevant two different instructions regarding sums, visualization, sums of it. Again, our slicing criterion is a value of I in the printf, right? So we can basically define this simple language. And by the way, so we haven't talked about the parsing that much because this is grad core, but the fundamental theory for the parsing is, or to facilitate compiling implementation of any language, is based upon so-called context-free language and context-free grammar. So if the language basically satisfies just context-freeness, then we can mechanically and systematically easily build corresponding parser. So that was a kind of our first homework we didn't do, technically. But this is a really simple language grammar we call matched parenthesis language, okay? So here I just use I because I have infinite number of call sites, right? So no matter how many, I don't care. Each time I encounter this call site, I'm assigning this different I. Like the way we basically naming each variable in the same single assignment form, okay? So then of course, anytime the function gets returned, we expect which one? If we start, let's say, I thought that was one, then I'm expecting whatever that one's subscript over closing parentheses. Okay? But then the nice thing about this context-free language formulation of a feasible and infeasible path is that dynamically, while you're following certain edges, you can basically dynamically decide whether I need to follow this path or the other path. Then you can do this on-demand analysis by having some changes over the original grammar. Because this one is something that you know at the end of your task or part of the actions you're putting dependence graph searching for the backtracking, right? But dynamically you basically decide, do I need to follow this path or do I need to skip this path by having these things? So while we don't see the closing paren because I haven't even visited it yet, right? But still, I'm able to say, is this the path that I need to take or not? So that's the kind of example. So if we follow this thing, again, this is not parentheses to match it because I started with an old paren, I ended with bracket. So my partially match the grammar, context-free grammar says, right, you should not actually consider this thing. But what if I consider the other thing right here? Okay, so then we started with these opening reference. Then you just see the closing parenthesis right there. That is the language, your context-free grammar we saw in the previous slide, which is 3 lines of a grammar rule. Except that's the basically the path you needed to follow during your independent practice. So again, that was a kind of interesting point. We had a kind of questions, right? So here in this case, which one do we need to follow? Because we studied this path right here. That means I should go this path because that's the only way I can match these parentheses and I can do this thing dynamically decide. When I get to this point on demand, I see I know I should not go to that path. So then you can just follow the rest of the backtracking. So that was a kind of the places right here. When you get to these places, then you should not go this way, right? You basically go this way. If you study from this, sorry, so this is basically our slicing criteria. So when you go through these things, then you have this parent. That means when you get to this point during your backtracking, you know this is not the path. Because you assign for this cloci, some different types of or different variants of the parentheses. So anything that is highlighted with this thick arrow is basically part of the edges you're tracking during this context-sensitive system dependence factor. So eventually, you get this thing, then you basically get rid of, then we don't include it. So here, the gray part is something that we don't include, we don't see at the end of the day for the resulting slice. But again, this is basically the way we basically get rid of the imprecision. But let's do purposely ignore this context sensitivity. So what things are happening? Let's take a look. You already know this has nothing to do with this ice value. So this is a kind of the our system dependence graph, but this time we don't care about this context-free language and context-free language pass parentheses match the pass. We don't care. Okay? We just mechanically follow it as long as I have incoming edges, right? So then what would be the result? We're doing on purpose. You can see this guy was my interesting slicing criterion. Keep following right here. Of course, I follow these things as well. But when I follow this guy, then I end up having this guy. I end up putting this call. I end up putting this sum. That's why these two, which we already know, they are irrelevant for the i's value in the pre-net. We end up having that. Why? Because we ignore this context sensitivity. All right, so there are many other usages, especially for the security domains these days. So raise your hand if you have heard terminology like static taint analysis or taint tracking or dynamic taint analysis. Raise your hand. Anybody from security? No? Okay. Let's say we have some security critical code, okay? But whatever the variable that is referred by the security critical code is coming from whatever the one variable data is originated from, let's say some outside of privilege mode, such as user provided there. Like the SQL SQL query attack, okay? So that's why whenever you have a sum outside of the values being propagated, we basically taint, right? This is something that is originated from outside of privilege mode, like a user code. And then we basically keep propagating the taint. Let's say I taint A, but then here's a code, B goes A. So that means B is also dangerous as well. This guy is a taint. Okay, then anywhere places where now the B and A are both used, and whatever their target is also tainted. So then when you get to eventually the security critical code for any variable you're gonna accept, you basically check the taintness of the variable. If you end up seeing that any variable you gotta access is tainted, well then that's dangerous because that value is originated from some outside of the privilege mode. But I talked about this thing, the taint kind of concept. The creator of the taint analysis in the UC Berkeley, she's not a compiler guy, but I bet if she took our compiler course sitting right here, then she wouldn't have created this new terminology, static analysis. This is what exactly our forward proven slicing does. If you Google, or let's say Stack Overflow, what is the main difference between static tainting and forward proven slicing? There are many wrong answers, but they're technically the same. But static taint analysis, they only care about the data. They don't care about anything about the control structures. But in a sense, our forward slicing is kind of subsumed what the taint analysis is trying to achieve. Okay? So static taint analysis, that's technically our forward ripple effect analysis for slicing. Okay? And then we can use the slicing to find some vulnerable code detection. We already know some code pattern is vulnerable. Then we have a slice, and then probably any variable in the other code that I don't know whether that is vulnerable or not vulnerable, get the slicing. And compare these two slices. If you're kind of closely match each other, there's a possibility that code is also vulnerable. And for that, our plagiarism detection tool must be developed by the guy in the UC Berkeley using these proven slicing. I mean, he almost abused this slicing very much to detect the clone code real copy. And we sometimes do code obfuscations because I don't want anybody to understand this code. But no matter how you're gonna basically obfuscate the code, see the dependency is there. Why? Because dependency is basically the semantics of the thing, right? But I mean, this is one way you can basically understand this encrypted code. So that means that you can possibly break certain level of this code obfuscation level. And we can do the formals as well. So this is something that I promised in the last lecture. We can use the slicing for the formals. And everybody know if you have a memory access for the modern computer architecture, it could have been 1,000 cycles so easily, right? So probably I don't have to repeat why. But because of that, between the processor and the memory, which takes more than 200 to 300 cycles depending on which server architecture you're going to talk about, we put the SRAMs right here. So your memory is DRAM, right? SRAM is much faster, and this is closely located into your processor. So that's why if you have the data in there already, then if you access the cache, then you save hundreds of cycles. Okay, that's what the cache means, right? But then let's say some applications data footprint is so large. Why cache we created? Because there is so-called locality. You have access to data, if you fetch the data from the memory to the cache, then more than likely in the near time you're accessing it together. There's some neighboring one. I just explained the temporal and the spatial locality. Okay? That's why we have a cache. But let's say some application causes so many cache misses. The number one reason why that takes so while is because it ends up with so many cache misses. Okay? So then how compiler and you, the compiler architect, solve the problem? You're both basically telling you, use compiler optimization to get rid of these cache misses. How are we going to do that? So one idea is prefetching. Before you access, let's say this guy is basically the instruction for the load, accessing. I don't see there, that's why I have to go to memory, spending 300,000 cycles. Okay? But what if we can bring the block from the memory to the cache before this guy is accessing the cache? Then they will find the data in the cache means it's gone, right? But this can be done with compiler optimization. So that's the problem. I'm not happy, so I need to pay the 1,000 cycles right there. So now I'm running this application with compiler generated slice that I call hyperthread. And this guy is the one that helped this guy access the memory faster than before. That's why I call it as hyperthread. Okay? So this is basically the slice of, or the code of the hyperthread, the slice of original code. Maybe that's a better way to say it. Of course, I need to have that memory instruction because that is the one that causes cache misses. So I'm executing these things together, then slice is usually shorter than the original ones, right? If you start let them fight each other, which one is the faster? More than likely slice one because slice is usually smaller than original code. So meaning there's high chance this guy access cache or whatever the memory block before the application is ready to get to this corresponding memory operation, which is the case right here. So of course, still you don't have anything in the cache, so we bring the block from the memory, but while we are actually fetching the block, your application thread still executed in parallel. This is kind of multi-threading, right? And then when you get to this point, when this guy is accessed the memory, of course we need to see the cache first. All right, I see the data in there. That way I can save the times right there. This is basically the main idea of the helper thread prefetching. And you can do this on your own. we have multi-core processors, right? You can assign the one thread right there where you want to accelerate by eliminating its cache misses. But you need to run this thing in the near core, assuming that they eventually share these L2 or L3 caches. Meaning when they access this L2, maybe there's cache miss, but with the help of thread, you basically fetch the data from the memory to the L2 caches right here. And even we're talking about this, say, intelligent memory, processing in memory, meaning in the DRAM, you can put the little processor in there. So that means that you don't have to basically do the process and fetching the data, processing and the writing data back to the memory. You don't have to do it because you already have a processing unit in the memory. So this is the benefit of the so-called processing unit. But even this kind of an intelligent memory architecture, you can leverage multi-thread. So application thread usually running upon the your host main processor. You're gonna run the slice of it in the memory processor. Of course, when you run it, Alpha thread basically fetch the data from the memory before your application thread access. But here in this case, you just read the data from its local cache. It doesn't do anything to the application thread, right? That's why you gotta do something additionally right here. You fetch the data from memory to its memory processor cache, and at the same time, you put that into the host processor's caches right there. The whole purpose is before the application thread demands or asks for it, I will bring the data to the L2 cache so that it becomes cache hit. So then the question is, how can we basically construct these algorithm thread code? Of course, whatever that memory instruction that causes cache misses, there must be something we have to keep it in the helper thread, right? Otherwise, it doesn't actually bring the block from the memory, right? But that's technically prefetch instruction, which is nothing but load instruction. But it doesn't generate any exception, any speculation error, but technically load other than that. So you have a load instruction parameter, and whatever the parameter, it's not constant, meaning whatever the load address is generated by some other instruction. Let's say, to get to know the cache block address, memory address, I need to execute these yellow instructions. So this is data dependence, right? When you follow data dependence, that means here in this case, anything that is effective for address calculation for the prefetch must be part of your slice set. Of course, what if you have so many dependencies? Then the problem becomes now backward slice. Okay? This is exactly my compiler did almost 15 years ago. So we have the code. This is basically MCF code that we often use to evaluate the performance of the processor. This is Spec 2017 benchmark. And so here, let me just kind of skip it. I know somebody already trying to leave, but that's basically the code that generates a whole bunch of cache misses. How do we know? With the profiling. And then anything that has dependence, now you build a proven dependence graph. You then mechanically following all these things. So here I didn't actually show the proven dependence, not to make the slides crowded. Then anything that is not in the proven dependence can be eliminated. So eventually you change these cache miss generation memory instruction in the prefetch, and something redundant should be eliminated. And if you look at the final code, that is way smaller than the original code. So that means if you let them start from the same places, then this guy is getting way faster than the application thread. That means this guy is the one that prefetched the block on time before the application thread gets to access the memory block. And this is the way you can eliminate the cache misses, and compiler makes critical role by leveraging backward proven slicing. That's what's going on.